In this video, we're going to begin our discussion on infix, postfix, and stacks. So we're going to continue looking at instructions, and these are going to be instructions that do some kind of calculating. And so we're going to be looking at the syntax of the opcodes and the operands. So we've said on a number of times that an instruction has an operation or opcode, the description of what is to be done, and then there will be data. And we've talked about different kinds of data, different kinds of operands. But here, our operands are all going to be of the simple sort of the immediate kind. So if you see a 4, that's not memory location, not some value indicated by memory location 4, but it will just be immediately 4. But we are going to talk about the syntax, the ordering of the opcodes and the operands, and that's what is our main focus here. So if we're taking a simple operation of addition, and it's going to have two operands, the two numbers that we wish to add, then there are sort of three ways to arrange the syntax to the opcode and the operands. So we could have what is called postfix, where we could have the two operands first, the 4 and the 5 that we're adding, and then the operation, the opcode, the plus sign in this case. And we will say that that is a syntax that is good for hardware and works well with stacks. So that will be our preferred approach. Another arrangement, another possible syntax is prefix, where we say it is addition that we are going to perform, and then the two pieces of data are the 4 and the 5 follow. And then the infix version, this is probably the version that we're used to sort of seeing, and that has the opcode between the two operands. All right. And then in any kind of calculation where there is just more than one operation, then we have to worry about precedence or order of operations. So if we have multiple operations, we have to worry about the order in which they will be done. And this will be handled differently in postfix. So here we have a simple operation in infix, 1 plus 2 times 3 minus 4, but then we must remember our order of operations, our precedence. And so we know that the multiplication is to happen first in this case of the operations. The multiplication has the highest precedence, and so the 2 times 3 is done first, and then the addition and subtraction have sort of equal precedence, but then we will make some rule. In this case, we will start from the left and work our way over. So we will say the 1 plus 6 and perform that and get 7, and then finally subtract the 4 and get 3. Okay, now we want to convert this longer expression, not just a single operation, but the three operations. We want to convert it over to postfix. And so we want in the end to have postfix where we don't have to worry about the order of operations, that they're sort of like built in. But in order to get there, I sort of almost overemphasize the order of operations. And we will see eventually a better, more efficient way to do this. But for now, in these sort of simple ways, we're just going to really sort of overemphasize, put in tons and tons of parentheses to really overemphasize the order of operations, and then um, create from that this postfix. So in moving from infix to postfix, this will be our first cumbersome approach. So in as we just saw, as we were doing the infix calculation, we said the 2 times 3 was the first operation, so I put parentheses around it. They were not necessary, but I'm just overemphasizing the order of operations. And then I added the 1, so I put a set of parentheses around that. And then finally I subtracted the 4, so a final set of parentheses. And then I start working from the innermost parenthesis and converting it into postfix. So I change, you can see there in the middle of the slide, the 2 times 3 I've converted to 2 3 times. And once I've made a conversion like that, then I'm going to think of that result as a number. So once I've made 2 times 3, 2 3 times, then I'm not going to perform that. I'm not going to get 6. But what I'm going to do is treat it as if it were a 6, as if it's a single number. So nothing's going to come between the 2 and the 3. Nothing's going to become between the 3 and the star. It is now sort of a unit corresponding to 6. So now I look at my next set of parentheses. So once I convert to postfix, then I will get rid of like one set of parentheses. So the 2 3 times, now I'm throwing out that parenthesis, and I have 1 plus 2 3 asterisk 2 3 times. And now I will make that conversion and make that one sort of number operand opcode. So I will make that first operand 1, the next operand 2 3 star, and then the opcode, the plus, sort of moves after the operand. And then for the last one, I now have the 1 2 3 star plus. That is now in postfix. I will not touch it. Nothing will come between those things. And then I have that minus 4. And so then I will finally put that in a postfix ordering. And so it'll be operand, app code. And so then it will be 1 2 3 star plus, treating that like it's a number now. The first operand, then 4, my second operand for the subtraction, and finally then the opcode at the end, the minus, and then there are no parentheses in postfix. That's one of the nice things about it is to get to the postfix, you've dealt with the order of operations, and you don't have to worry about it once you get to postfix as opposed to infix. And so then get rid of all the parentheses, and I will have the postfix expression. So here's just another one. And sometimes you can work a little bit in parallel. So I have, in this example, it's a longer one. I need some parentheses in the original expression here because I want to perform the 2 plus 3, the 5 plus 6, the 7.8. I need to do those earlier than multiplications they are used in. And so in order to force that addition to occur before a multiplication, I introduce parentheses that have a higher precedence or a higher order of operations. Okay, so I am taking, again, sort of over parenthesizing this expression and to emphasize the order of things. So I had the 2 plus 3 times 4, that will be an operation. The 5 through the 9, that will be some operation. So I'm adding parentheses, bringing in the 1, then bringing in the whole thing. And then within any sort of set of parentheses, I can sort of go to the innermost. So I can do things a little bit in parallel. Again, this is not the efficient method. This is just us trying to sort of come to terms like a first round with converting infix to postfix. So let's overemphasize the order of operations with all these parentheses. But within these sort of multiple sets of parentheses, I can go to the innermost and convert from infix, which is operand, opcode, operand, to postfix, which is operand, operand, opcode. And so I've used some color here as well. So the innermost parenthesis near the beginning is the 2 plus 3, which I've changed to a 2, 3 plus. The 5 plus 6 became a 5, 6 plus. The 7 plus 8 became a 7, 8 plus. And I made those now red to say that much has been converted to the to postfix, and pretend from now on that it's a number, and don't put anything inside there. The 2, 3 plus should now be considered like it's a number. And if I were doing this, if I were writing it out, then I might sort of underline them. So I can use red here, but I would come up with some other notation like underlining if I were sort of working it out on a piece of paper. And so I'm just sort of carrying on working out from my innermost parentheses. So the 2, 3 plus times the 2, 3 plus unit times 4 becomes 2, 3 plus 4 star. The 7, 8 plus unit times 9 becomes 7, 8 plus 9 star. Again, the 7, 8, 9 now is already converted, so we think of it as an operand. And so we have operand 7, 8 plus star is the opcode, 9, that's in infix, and we're changing it to postfix. So it's 7, 8 plus, first operand, 9, the second operand, then the star. And then we're, again, working our way out. One more set of parentheses. So we had in the front there 1 plus something that was already in postfix. And so it became 1, that thing that's already in postfix, and the plus operator goes to the end. And the same thing, we had 5, 6 plus, and a multiplication sign, which was still black because that was still infix, and then the 7, 8 plus 9 star. And then we move the number 5, 6 plus, that's the first operand. The second operand, 7, 8 plus 9 star, that's the second operand. And we move the opcode, the multiplication, to the end. And so now we have just, there is 1 black plus still left, and then we convert it, can make that last infix to postfix calculation by moving that plus to the end. Okay. So that is the game of converting infix to postfix. Another time we will do a more efficient way to do the conversion. All right. Why are we going through all this? Because postfix is better for hardware. So eventually you want to, in your architecture, you have the ALU. That's where arithmetic and logic operations take place. And you've got to get the data over there in your like fetch and decode and fetch data and execute. We need to do fetching first. We need to get data first, and then we can operate on it. Then we can perform some addition or subtraction, multiplication, anding, oring, excluding oring, but we have to get the data first. And postfix sort of prepares us for that it has the operands first. And then we say that it is one way to do this calculation is known as a stack. And a stack can be a hardware thing or a software thing. Um, and it has a place. The stack is a data structure, is one way to think about it, but it has a way of holding information, but it has a limited way of accessing the information. And that's what makes it a stack versus just random access memory. Random access memory, you're holding a bunch of things and you can access any of them, quote unquote, randomly. With a stack, there is this level of control. You stored a number of things, but you are limited in the way that you can access them. So the stack data structure, we say, obeys a LIFO protocol, a last in, first out. So we can add data or take away data that we are putting into this stack, but we are limited in the way we access the data. If we are adding data, there's only one place to add it, the top. And if we are taking data away, there's only one way to take it away. And that's also, again, from the top. And so then if we are taking some data, we are taking it from the top, and that is the thing that we just previously added. So that's what we mean by last in, first out. The thing that we are going to take out, the first out, is the top, but that was also the way we write it, was the last one in. And then we have some special terminology. So when we are writing something to memory, we call that a push. And when we are taking it, when we are reading it, we refer to that as a pop. Okay. So here is just a simple picture of a stack. And so we put a number on a stack, in this case, a 1. And then we put another number on a stack, in this case, 2. And then we are showing that we have taken a value off the stack, in this case, the 2, but the 1 remains. And now we have put a 3 onto the stack and then a 4 onto the stack. Let's just bring in the idea here of the stack pointer. So we said we have this limited way of accessing the memory, or accessing these locations. So in RAM, in random access memory, you supply an address and that you can get the data at any address. In the stack, you can only work with the data indicated by the stack pointer. So in this example, the stack pointer is indicating or pointing the next available slot. So in that leftmost column there, we have the 1 on the stack, and our stack pointer is pointing at the next available location. And I'm saying X. There may be something in there. I don't know what it is, so I'm just calling it X. And then we have pushed on a 2. So that put that 2 in that spot we were pointing to, and it changed where we were pointing. So now we are pointing to the next available slot. Then as we move from column 2 to column 3, this is sort of as we progress in time, we are popping the 2, we are reading the 2. So we took the 2, whatever we did with the 2, I have no idea, but we did something with that 2. We had it on the stack for a reason. We took it off the stack for a reason. We did something with it. We didn't have to erase it from the stack. It can still be sort of sitting there. But the way our access of the stack works with this stack pointer, that location is a location we would write to, but not read from. So that 2 may still be sitting there in the middle column, but it's not really accessible. We have already popped it. And so the next action was a push, and so the 3 overwrote the 2, and it moved the stack pointer to the next available slot, and then we pushed again with a 4, so that again went to the available location and changed the stack pointer so it's pointing to the next available slot. So that is our idea. We will continue with this in another video. Thanks for your attention.